So with this dimension constraint that you can observe in the parameter tab, we have different dimension constraints that can be applied. We have the linear dimension, align dimension, angular dimension, radius and diameter, and also we have an option to convert. This symbol is used to convert the existing dimension into a dimension constraint. So one thing that you have to notice that when you apply a dimension constraint onto an already constrained object, then you might get an error stating that it's going to get over constrained. So for example, if we want to apply this linear constraint for this point, you can see that the AutoCAD throws out an error stating that the current dimension constraint that we'll be applying will be over constraining the geometry. Why? Because we already have other constraints that are applying here. So we can also remove whichever is not applicable to us, or that is, we can create a reference dimension. So the reference dimension is going to be driven dimension. That is, it's not going to modify the object in any way, but it's just used in an expression to control other terms. So it does not constrain the geometry of the object, but that is not intended to us. So for that, let us just remove these dimensions. We'll remove all the dimensions that are linked to it with this thing. You can either click in by this into mark or right click and then click on delete. So these two ways are how you can eliminate the constraints, because earlier we had used auto constraint. So let us now remove everything and then create dimension constraint as well as geometry constraint that are of priority. So first thing is like, we'll go on with the dimension constraint. That is, we are applicating the edge of this hexagonal. This is going to be the first dimension. So this D is going to be the nominal diameter of this bolt. So let us just name this as the as a geometry constraint here. So yeah, so let it be here. Then we can modify it. We can modify it in the parameters manager. But right now, this is the first dimension. So next we are going to constrain this dimension of the circle and followed with by the dimension that represents the pitch. So having said that, next we need to correlate. Using this we can correlate the dimensions. So now we'll apply the equal constraint to all the dimensions, so that whatever this nominal that we have set will get applicated to the all other objects also. So we are going to apply this equal constraint. So now we are doing the manual route. So it means that this polygon shape will be controlled with respect to this dimension. So next we have to constrain this circle. So wherever this dimension is going to update and this polygon is going to update, this circle that represents the chamfer cut needs to get aligned for all. So we have to assign tangent restriction to all the contact points, that is all the edges of the polygon. So the difference between this and the auto constraint is that we are applying the dimensions only that is of critical use to us. So you can see it already shows that it is getting over constrained here. So let us not give that. So next, finally, we have to give a concentric dimension control. So with respect to the inner circle, we will assign these two, and then again with respect to this and this outer circle. So thereby given all the constraints that are required. Now let us look into the parameters manager. So here we have different tabs or the columns that describes the parameters. You can add or delete it by right clicking on here. Right now all of them are selected. So we have the name, expression, then the value that is already there, the type of the dimension constraint, and then description if required. So here you can see that we have D1, dia 1 and dia 2 that are constrained. So you can rename it. So this D1 is going to be the nominal diameter represented by D. And the second dimension, this is dia 2, that is going to be the pitch. It also phenomenologically going to be equal as the same dia. sorry, let it be D1, but here what we want to do is we have to keep it equal to D. So it means that D1, that expression is D, so that whatever value we have it here will get reflected here. So simultaneously this diameter, let us name it as D2, this should be 0.85 times of D. So now these are the expressions that we are controlling, that is, these are derived dimension based on this base dimension. D1 and D2 are derived based on this base nominal diameter D. So this is how we parameterize the dimensions. Now let us close this out. So now let us see how we can use this. So let me just copy and paste it here. Okay, so now let us see how it's going to vary here. So say let us go for a approximate nominal dimension of 12. So you can see that now this hexagonal nut has got updated accordingly. So all the dimensions that we have here based on the geometric constraints as well as the dynamic constraints have been applicated, and the same has been updated. That is, this diameter and this diameter is going to be the same, whereas this diameter is 0.85 times of this diameter. So this is how use the dimension constraint and also the parameters manager to apply the different variations. As you can see here, the parameters managers now has got updated with the columns that you have here. So here it has got updated that this D3 dimension is equal to D5 and this D5 is the base dimension, that is D. Okay, so it has, the numbering has been made based on the previous dimensions that are available. If you could recollect, the base was D and we had selected D1 and D2 to represent the other dimensions, and AutoCAD subsequently allocates the next dimension numbering as a sequential numbering, but all the parameters that are already constrained get applied to this. So this is how you can use the dimension constraint to use it and then save it in the drawing, so that you can modify the drawing based on the different requirements that you have. So this summarizes the dimension constraint that you can apply onto your drawing.
So once you have defined your block, the next step is to write it to a file so that you can reuse it later. So that function is called as a W block, that is, write the block to a file. So the selection of the block is either through the already a referenced block that you have created, or you can store the entire drawing as a separate block, or select the objects as you do in the creation of a block object. So you have similar coordinates here. You have to select the base point, and then the next step is to select the objects and to either retain or convert to block or delete from the drawings. And then finally, the destination address where it has to get stored. So this is how you write a block. So suppose we'll take a block, the hex nut, and then store it as a drawing here. Okay, and then also specify the units to it. Always make sure that you have the correct units specified, because this reference is later used for you in order to scale the block as required based on the drawing that you have. So based on that, you can click on OK to create a drawing. So here now the block has been written to a separate file so that you can refer it outside this current drawing. That is, if you open up a new drawing, you can still refer to the existing block that has already been created and work upon. So that is the W block function. So next we'll quickly look into how this block, what we have constituted, is going to help us in modifying the text. We had seen already the dimension constraints that will help us to modify the block properties. Okay, so let us look into one more again and look into what is that constraint it talks about. So if we try and insert the block now, so you can see this is the hexagonal nut that we have created. Okay, So even though the reference of this object is the same as here, you can see that you don't have the flexibility to edit the dimension references that you had. And also if you update the dimension references, so what happens is all the block references, that is all the blocks in this drawing that bears the same name, will get updated when you modify this drawing dimension. So in order to avoid that, we have one feature called as a dynamic block settings. So here we can modify the block dynamically using certain key parameters that we wish to look. So we'll go ahead and do it. So what we'll do is we'll edit the block that we have here. So in order to edit the block, we have the block edit command. So it's either bedit or be. So once you do that, it asks for the block that we need to modify it, or you can also create a new block and then edit it. So now the objective step, we have to modify this block so that we are creating a dynamic block reference here. So we select this hex nut and go ahead. So now you can see that we still have the block editor object that we had seen during creation of the block, but with an extension of commands that is available. And we also have a floating palette that is available. This is a block editing palette. So we'll quickly look into what are the different options that are available in this block editor. It's also a specific dynamic ribbon that is open up only during edition of this command. So what we have here is we have the edit block command and then also save the block definition to a file. Then we can also test the block before execution so that it will open the test block on a separate window so that we can see how it looks and how the dynamic commands that we have given will look like. We can do all the variations. Next we have two of the previous use reference, that is we have the geometric references and the dimensional constraints, geometric and dimensional constraints, and also we have one more thing called as a block table. So here we'll define the properties of the parameters that we are looking into. This will create the dynamic input to it. So we'll look into it very detailedly. So next we already had this parameters managers looked at, and additionally we have the authoring palettes that we have, and then we also have one more powerful functionality called as an action parameters. So the action parameter defines how the geometry of the dynamic block reference is going to move or change when the block is modified, so that we can add the actions. Okay, so we have different actions. Those can be assigned to blocks wherein we must associate them with the parameter and the geometry. So this is what the action parameters look like. So we'll look into that in detail. And then also we have the attribute definitions. So this attribute definition is used to specify the properties of the attribute and the prompts that should be displayed when the block is inserted. So it means that it's a label or a tag that's going to get attached itself to the block. So it's a data set that will attach to the block. So that what we can do is we can give additional info to the block. We can assign part numbers or the component specs or prices or comments or what is the creator name, all those things. Those references can be inserted along with this block that is created. So this is the attributes that you are assigning to a given block, so that these can be used as information that can be used to cross-reference, example your bill of materials and so on and so forth. And also these attributes are only visible for information during your editing or drawing operation, and during plotting it won't be visible, that is it is invisible to your plotting operation. However, these information is going to store in the file. So we'll look into it again in detail. So next, finally, we have another important functionality that we can use it to our flexibility. That is, we can create visibility states. That is, based on the selection criteria, we can either make block object visible or not. So we look this with an example to get it more clarified. So just put it together, all the functions that we have. Here is the block editor is going to be a contextual tab that is only when you are going into the block editor command, it will open up, and we have the special ribbon wherein we have an option to provide the constraints, we have option to give the parameters, we have options to give an action specified, define the attributes, then manage the visibility states, and also save the block definition. So this is the overview of the block editor that we use to create dynamic blocks. Okay, so now we'll quickly look into what are the different actions that we can do or the functions that we can do to create a dynamic block. So as and always, we have the parameters that we have to define to generate the relations between the object. So even though we had created dynamic constraints earlier, dimension constraints, those are pertaining to the drawing view only. But if you go into the block editor, you can't see those commands. So that you have to create the geometric and the dimension constraints into your block definition. So we'll try and do it again using all the commands that we have. So first thing is like we have to give the equal constraints to all the sides. So having given the equal constraints, so next we also make sure that the sides, the opposite sides of the hexagonal nut are going to be parallel to each other. So in certain cases, you can see that the dimension has been over constrained because with this reference and with this equal signs, the figure gets constrained to each other. So in that case, AutoCAD prompts that the figure is already over constrained. The constraint cannot be applied because it conflicts with an existing constraint. So in that case, we can proceed with the next constraint that we have to do. So the next constraint is constraining these circles, the inner and outer circles as concentric. So with this, we have applied the basic constraints that we have to look at. So next is, we have to apply the dynamic constraints. So we'll go ahead and give the dynamic dimensions here. So we have one linear dimension, and then we have the diameter constraints. Okay, so after applying this, we just have to look into all the constraints that we have already applied and see whether it is possible sufficient. So what we've done is for the sides of the polygon, we have applied equal constraints and also parallel to one of the faces so that the overall structure gets optimized. But then also we have one more constraint we have missed out. That is, we have to make sure that this circle, the outer circle, the chamfer circle is going to get tangent to the sides. So we'll apply that to all the sides. The other way of verifying whether the constraints are sufficient or not is by testing the block, and by varying the parameters you can see whether the constraints are sufficient or you have to assign additional constraints or not. So having said that, having applied all the constraints and having set the dimensions, again we can go into the parameters managers to look into what are the various constraints that we have. So we'll do the same assignment of the constraint as earlier. Yes. So with this, we've applied the constraints to here. So now the next option what we have here is the block table. So this is where we can predefine the the list of options that we have. So once we click on it, it will ask for the position to position the block reference, and next it will also ask how many grips that are need to be placed. So grips are the dynamic editing options. So we are proceeding with a single grip. So we can get the block parameters properties table. So here we'll insert a new properties. So which is the base reference that we need to have? So this D1 is your nominal diameter symbol, the horizontal dimension constraint. So we'll use this. Okay, so here what we can do is we can give a predefined set of parameters. That is, we can say I have the major diameter of 5, 8, 10, 12, 15, and so on and so forth. But let us now consider the 5 major nominal dimensions, and now we can click on OK. So now you can see that the block table reference has been created, and also a dynamic editing grip has been created. So now we can test this block, how it looks like. So when you go ahead and test the block, so here we have the block reference. So now you can select the block, and once selected, you can see that you have a down arrow button that is available here. This is your editing grid. Click on it, you can get the different options that you have. So you can see that the base reference what we created is highlighted with the tick mark to it on the left side, and if you want to modify it, you can see that the object gets modified accordingly, and our constraints are holding good so that these basic reference is withheld. So likewise, what we can do is we can optimize it. But when we go for a lower dimension, you can see that the sides are not getting reduced, but the circles have to get reduced. So it means that our constraints are not sufficient and it's getting rotated. So if we need not have this rotation give a horizontal constraint to this plane, and also what we can do is we can fix this point so that that reference gets constant, so that with this reference and this tangential sign we can assign the operation. So now let's test the block again. So now the constraints hold good. So this is how you test the dimension and geometric constraints that you have assigned for various dynamic block references that you have. So this is how you assign the different properties to it. And next we have this attribute definitions. So in this attribute definition, we have different options that you can associate with the block when we are going to insert the block in the drawing. So the first is the invisible setting, so that it specifies that the attribute values are not going to be displayed or printed when we insert the block. So we also have a system variable, that is ATT display, to control this invisible mode. So next we have the constant option. So this gives the attributes a fixed value for block insertions. And next we have verify. So once we selected it, every time it prompts us to verify that the attribute value is correct, so that we can have a checklist kind of thing. So when we insert the block every time. Next we have a preset condition, so that it always sets the attributes to its default value when we insert the block containing a preset attribute. Suppose the preset attribute, say the block reference is going to be of X dimension, that can be set as a preset, and hence every time the block is going to get inserted, only that preset variable will get called upon. So next we have the lock position. So it means that the location of the attribute within the block reference can be locked, and when unlocked, the attribute can be moved relative to the block using the grips that we have. So next we have the multiple lines. So here the attribute value can be specified with containing multiple lines of text. So when this option is selected, we can specify boundary width for the attribute that we are going to define. So next we have the insertion point for the attribute block definition. So that is a given norm. Next we have the attribute definition data. So we have three categories. We have the tag, the prompt, and the default data. So this tag is going to identify each occurrence of an attribute in the drawing. So we can enter the attribute tag using any combination of characters except spaces. So this is going to be the reference, the nameplate to this attribute. So next we have the prompt. So prompt will be displayed when we are going to insert a block. So it means it's a floating definition that helps us to identify the attribute tag that we have. So next is the default value of the attribute that we have to specify. Next we have um, the text settings. So in text settings again we can define the justification and the style of the attribute block. So now let us just give the attribute definition as the. So for this material, let us for this component, let us define the tags that are appropriate for it. So this is going to be hexagonal nut. So the tags that can be used can be material, and then the nominal dimension, and then the cost. So let us try and insert these three tags to this block and see how it reflects. So the first tag that we are going to use is the material. So the prompt what we can give is enter the material of the nut. Okay. So the default material is going to be say stainless steel or graded steel. So we'll just give us a rough. This might not be correct, but this is just an idea. Okay, graded steel, and then click on OK. So now AutoCAD prompts us to enter the value, the position of this text attribute. So let's say we are going to paste it here. So this is the first attribute tag. So we'll call upon this second attribute tag again. Now it's going to be the nominal dimension. So there should not be any space between the tag elements. So here we enter the nominal dimension and say the default value is 8 mm, and then click on OK.